Toonyawat, and today Toonyawat Angkhanawin from Durham University will be speaking on graph coloring via quantum optimization on a Rydberg-Qudit atom array. So, Toonya, please start your presentation.
Okay, sure. So you can see my presentation, right?
Yes.
And also the cursor that I have moved around here.
It works.
Okay, sure. So hi everyone, nice to meet you all. My name is Toonyawat Angkhanawin, and I'm a PhD student from Durham University. And today it will be my very pleasure to give you all the presentation about my current work that just have been published in arXiv 3 weeks ago. The work is about quantum optimization for graph coloring problem using the Qudit-based Rydberg array. And if you have any inquiries about this work, you can just follow the arXiv link here. Yeah. So first of all, I need to thank my all collaborators. First, my PhD supervisor, Professor Charles Stuart Adams from Durham University, and my collaborators, Dr. Aydin Deger from University of Oxford, and my another collaborator from University of Clive, Professor Jonathan D. Pritchard. And we have been working very hard to make the works done and published in the arXiv 3 weeks ago, as I mentioned. And today's the outline of the talk will be the first one. I will try to introduce you the background of this work. Basically, it starts from the maximum indeterminate set problem solving by this Harvard group, but led by Mikhail Rukins. And in that work, they can solve the problems which is called the maximum indeterminate set problem with the qubit-based Rydberg arrays, and that will be the very first motivation of the works that solve the graph coloring problem with the qubit-based Rydberg arrays. And then the talk will be separated in two parts. The first part will be graph coloring problem, which is much likely to be the contents from computer science fields. And yeah, this is not my expertise, but if anyone have seen that I have been doing some mistake, and you can just feel free to interrupt me all the time. And the second part will be the Rydberg atom solver, which is quite a physics here. So normally will be the people in the atomic physics field would be familiar with this one. I will introduce you the optimization protocol, the physics, the essential physics of the Rydberg system, and how we encode the optimization graph into our Rydberg atom graph here. And go for the first section to the in the introduction of the background and the motivation. So as I mentioned, the work is more inspired by the remarkable experimental result from Harvard's group. In that work, you can see the link from this one by Bernin in the 2017 here. In that work, they prepare the Rydberg atoms in 1D chain, and each atoms here are coupling between ground and Rydberg states. Overall, Hamiltonian will be governed by this Hamiltonian. Basically, they got Rabi frequency, which is the coupling term, the detuning, which is the representing the energy of the Rydberg states, and the long-range interaction between the atom inside I and inside K if they are excited in the Rydberg states here. And you can see that this interaction is actually the van der Waals interaction by C6 over R to the 6. Yeah. Once they have prepared the atom in 1D chain, they perform the so-called adiabatic sweeping. You can see this is protocol that they were performing the adiabatic sweeping. First, they instantaneously turn on the Rabi frequency, which is this term, and then slowly tuned the detuning from big negative to big positive as a cubic sweeping function here. And with this adiabatic sweeping protocol, they can prepare initially prepare in the atomic ground state, product state here. And once they perform this adiabatic sweeping protocol, it turns out that the system can exhibit the translational symmetry, spontaneous symmetry broken phase. According to the lattice spacing of the atoms they adjust here, if each atoms are separated quite far away, it will be turns to be the C2 symmetry broken phase. But if we try to adjust closer and closer, this spontaneous symmetry broken phase becomes C3 and C4 respectively. So this is quite inspirative because somehow we can prepare the crystal phase in our Rydberg system. You can see that the C2, C3, C4 actually exhibit if you tune the detuning and the interaction length in the corresponding regime. You can essentially prepare the spontaneous symmetry broken phase as this paragraph as this diagram. And things become very interesting because you can see only I just want you to focus on this spontaneous C2 symmetry broken phase. It is actually the solution of the problem so-called maximum independence set problem. So basically, the maximum independence set problems is the problem that you are trying to find the largest set of the independent set. So what is this independent set mean? Independent set means that the sets such that all elements in this set are not connected at all. So basically, this is quite simple graph as you have the 1D graph, right? And each atoms are representing the vertex of the graph. And this graph only connected by the nearest neighboring atoms. So basically, each nearest neighboring atom are never excited in the same Rydberg state. So we call that the set of all Rydberg excited atoms here are independent because they are next neighbor atom, which is not connected by this interaction edge anymore. So this is why we call this C2 state as a solution of the maximum independence. And if we see it in more generalized version in 2D array, so you can see right now we prepare the same system as a Rydberg array, but just in 2D. And we want to solve this again maximum independence set problem. We just perform the same adiabatic sweeping as I showed you in the later slide, in the previous slides. We can see that right now the Rydberg state we will couple at the red dot here as the red dots here. And the sets of these red dots are actually the independent set because all the red dots here are not connected, you can see. And it's maximum because you cannot never have a larger red dot set larger than this set. Yeah, so we call this solution of the maximum independent set. And this maximum independent set have a natural connection to our Rydberg system. Why? Because our Rydberg system have the properties of the Rydberg blockade. The Rydberg blockade is very simple. It's just the neighboring atoms can never be excited to the Rydberg state because if your first atom excited in the Rydberg state, they will block the neighboring atoms such that the neighboring atoms can never be excited to the Rydberg state. For example, this red dot here, they are excited in the Rydberg state, and the neighboring atom, which is this one, and this one, they are just cannot excite the Rydberg state anymore. But this one actually can excite it. But because this one is excited the Rydberg state already, so this one cannot be excited to the Rydberg state. So that's why the solution of this maximum independence set are naturally encoded in this kind of system. So this gives us a huge inspiration. So what is the problem that can be naturally encoded in the Rydberg-Qudit system? Right now, we are considering just more than one Rydberg state. Some like we can have the red dots, we can have green dots for another Rydberg state, and we have yellow dots for another Rydberg state. And that problem is actually our graph curving problem, which I will explain in a couple slides. So the graph curving problem, I will first introduce the problem statement and the existing classical algorithm and their application in the real world problem. So if you have a graph like this one with the edge set 1, 2, 3, 4, 5, and with the vertex set 1, 2, 3, 4, 5, and the edge set is 1, 2, 1, 3, 2, 3, 2, 5, 5, 4, 4, 5 here. And the graph curving problem is that you try to coloring all the vertices such that no adjacent pair is assigned the same color and with minimum colors used. So it means that not just, so you can see that the solution to this problem might be this kind or maybe this kind, but the difference is that the first one here is not optimal because basically the red color here and the yellow color here can be reduced to the repeated color green and repeated color orange. So I would say that this one is optimal graph curving that we are looking for, but this one is not optimal graph curving, but it's graph curving as well in the sense that all the adjacent vertices are not assigned with the same color. But to solve this is just only NP complete problem, but to find the minimum color used, it's become NP hard. As I had said, I mentioned in this one, you can see the reference in this work, which is stated quite clearly. In order to finding the color used for coloring, the number of colors used for coloring a graph is actually NP hard, but the decision problem to decide whether the K coloring on the graph axis is NP complete. And the classic algorithm that widely used in these recent years is a greedy algorithm. So basically, the greedy algorithm is that you try to coloring them one by one and see if there is any conflict. If there is conflict, we just change the color to another different colors. So, but the efficiency of this greedy algorithm is depends on the order of the vertices to be colored. So basically, because you color it one by one, and the next vertex to be colored will be very important. If you choose it in the proper order, it might offer you a very fast approach to solve the graph coloring problem. But if you choose in the wrong order, it might take you a lifetime to solve the problem. So the order of the vertex to be colored is very important. So the very famous gradient algorithm is the Welch-Powell algorithm, which is right now they try to choose the order of the vertex such that they order from the highest degree to the lowest degree. So you can see the order here is a descending degrees. The degrees that I have mentioned is just the number of the incident edge of a vertex. For example, this graph, you can see that the vertex 2 have 3 edges. So we will say that this vertex 2 have degree 3. And this vertex 3 have degree 3 as well. But vertex 1, vertex 5, and vertex 4 only have degree 2. So if we align it in the order, it will be like this order: 2, 3, 4, 1, 4, 5. 1, 4, 5 actually are the same two orders. So we can just swap them whenever however swap is okay. It's just totally fine. So I just shoot 1, 4, 5 here. And then we first color the vertex 2 first with the green color, and then color the vertex 3. But the vertex 3 cannot be colored by green because they are connected to 2. Then we move to the vertex 1, but vertex 1 is actually cannot be colored by green as well because they're connected by 2. And then we move to the vertex 4, which is this one. The vertex 4 right now can be assigned the green color because they are not connected to 2. And vertex 5 cannot be assigned to green color anymore because they are both connected to 4 and 2 vertices here. So if we done with the first coloration, we just move them away from the graph, include the incident edge between them. And right now we got the subgraph 1, 3 and the independent vertex 5. And right now the order becomes 3, 1, 5 because 3 have 1 degree, 1 have 1 degree, and 5 have 0 degree. So right now the order of the graph will be 3, 1, 5. And again, we start from coloring the vertex 3 and then coloring the vertex 1, but vertex 1 is connected by 3. So basically only vertex 5 can be colored by the orange color. And the last one will be, we remove the orange set here, and we only left the vertex 1, which can be colored to the last color that available at this moment, which is the blue color. So the overall answer will be this one, which is optimal graph coloring problem that we are looking for. You can imagine that if you have the vertex with 100,000 vertices, you can imagine that how hard would it be to use this greedy algorithm, because actually what we are actually doing here is that we try to color vertex one by one in the order that we set. But this order, if you choose it wrong, it can cost you forever to solve the graph coloring problem. So there is another algorithm, which is the hybrid classical quantum algorithms. So the previous greedy algorithm is just purely the heuristic classical algorithm, but there are a lot of work that have been explored the hybrid algorithm, which is combine the classical and quantum machine to solve the problem. So the works done by this work, which is the work from the Pascal team. They have done the brilliant job. They explore to use the greedy MIS algorithm. So greedy still means that you solve the atoms one by one, but right now you try, because you know that the maximum independent set is actually the set that can belongs to one colors. So they try to solve the multiple loop of the optimization. The first, each loop here, we try to consider one MIS for each of them. For example, the first loop here, they consider the maximum indices for the orange color. So they got one, the set like this one. And the second loop here, we remove the orange set here, including their edge. Light, it's really the same as the graph, the greedy algorithm. We remove the orange subset here and do the MIS solution again. We got the set of the pink color as a MIS set problem. And then we remove the pink set, the pink subset, I mean the pink subgraph and the incident edge between them. And then we left and do the MIS solution problem again. We got the green color as a maximum independent set. And overall here can solve the graph curving. But it turns out that they found that this algorithm is not efficient because sometimes the curving set not necessarily belongs to maximum independent set. They can belongs to the so-called maximal independent set. Maximal here is means that you still got the independent set, but this set is not the largest. Maybe it's smaller by 1 degree or 2 degrees. I don't know, maybe, yeah. And they do this bench and bound method with this maximal independent set, where each node here, you can see the bench and bound 3, right? And the first is, you can consider each layer here as a node. So this is the first node, this is the second node, this third node, and fourth node. And each node will contain the subgraph, which is actually the subgraph of the problem that have removed the maximum independent set from the previous node already. So for example, we got the first node here, which is you got a original graph, and then you solve to find the maximal independent set. But right now, you consider multiple MIS solutions. For example, from this graph, we can have 3 maximal independent solutions. And these 3 solutions will generate a branch for the branch and bound method. And each band here still, they got the MIS solution and then remove that that's maximal independent set subset, remove it away. And the remaining of the graph solve the maximal independent solution again, which is got for example, this branch got 2 MIS solution, and they do this branch again and again until there is no vertex left for coloring. And you can see that they will, because they are branch and bound method, they will have some pruning criteria to eliminate some trajectory. For example, this trajectory can be eliminated if they are not satisfied this pruning condition. And the trajectory that left with the smallest layer will be our graph curving solution. Basically, the number of the layer here is actually the number of the colors we use. And the layers with the smallest layers, it means that they use the minimum number of the colors, and that should be the solution of the graph curving problem, or I would say the minimum vertex curving problem that we are looking for. And there is a lot of real-world application for this graph curving. The first one is electric vehicle charging optimization. As you can see that nowadays we have EV running in the roads, and there is a lot of company that try to, it's become popular as a product because it saves energy, it doesn't make any pollution. So right now, a lot of people begins to use the electric vehicle. Yeah, but the problem is that how we can manage the charging station to this to the regions that the people use the electric vehicles, because it's quite if you didn't manage well for the charging station to be localized in some space, it might be that some station would be overload in their work, because a lot of cars will be overloaded on that station only, but not distributed to another station. So that's become the problem. So the electric vehicle charging optimization is that, for example, I will show you this paragraph, this diagram here. We have 5 cars, and each car here will have a time window for the charging. For example, the first car will need to be charged from 9 a.m. to 5 p.m. And the second car need to be charged from 8 a.m. to 8 p.m., for example, and the third, the fourth, fifth car. And the only thing we try to do is that the car with the overlapping time periods, we try to distribute them to the different charging station. Because if they have the same period and they charge with the same station, it might become overload for one station, for one charging station, as I have mentioned already. So we try to implement the 2 cars with the overlapping time windows at a conflicting graph with the edge. with the edge connecting between them. So right now, the first and second car have the overlap time charging period. So we connect them to each other. And every graph that have, any pairs of these 5 cars that have overlapping charging periods will implement edge between them like this one. And we run the graph curving problem such that we got the red, green, and blue. Red, green, blue are actually the charging station that they need to go to do the charging. So you can see the 5 and the third car here, they can assign the same charging station because the 5 car is just the charging period from 2 p.m. to 9 p.m. But on the other hand, the 5 car is just only in the morning. So basically they are charging at different times, so they can assign to the same charging station. But for another car that have overlap charging period, they will assign them with the conflict graph, with the connecting edge, and run the graph curving problem, and then they will be assigned to different charging station. This is just one example of the graph curving application, but in the real world, there are still a lot of the similar problems such as scheduling optimization, logistic allocation, and even Sudoku problem that have the same similarity of the input and output problem and the constraint like this, the charging optimization. So basically, these 4 problems can be solved. I would say they can be mapped to the graph curving problem, and solve the graph curving problem would give the solution of this problem as well. Okay, the next will be the Kubo and Frio formulas. So the Kubo formula is quite, I think.
So sorry for interrupt. So this seminar is 30 minutes seminar, so maybe you can
speed.
arrange yeah.
Okay, sure. I will speed up the presentation. So the Kubo here. Yeah, the Kubo is that the form we use the binary variable XVI to introduce the penalized energy and rewarding energy. So basically, the penalized energy, the first term here is to prevent the adjacent vertex from having the same color. But we also have another term to rewarding the vertex to have the repeated color. And if we do the transformation from binary variable to integer variable, ni here is actually the projection operator to the Rydberg state, as I will explain in a couple of few slides. And we've got the QO, which is a quality unconstrained integer optimization, as have a 2 term here. And if we consider in the regime that B is bigger than A, this is the important regime where we solve the graph curving problem, because we want the penalized energy bigger than rewarding energy. So if we consider only the first term, this is a graph curving solution that we will get is not optimal, because you didn't add this term, which is responsible for maximize the repeated colors. But if you consider 2 terms, there will be optimal graph curving solution that you can looking for. We can say that this graph, because they need 3 colors, this means that this chromatic number of this graph is 3. This chromatic number is very crucial because they represent the minimum color used in this graph. And if you want to solve this graph with the Kubo or qubit system, you need 15 qubits to solve. But if you solve with qubit, you only need 5 qubits to solve. So you can see that we have saved a lot of space, saved a lot of resource in terms of the atoms to be cool in the chamber. You just need 5 atoms to be cool in the chamber, but it's qubit atom, not a qubit. And the last part of graph curving is the quantum annealing. So basically, quantum annealing is that you have the Hamiltonian of your system, and first you have the initialized Hamiltonian and the problem Hamiltonian, and you initially prepare the annealing state in the ground state of the H0, and then slowly tune the annealing the time parameters here, such that this annealing state stay at the ground state of instantaneous Hamiltonian all the time, and then they end up in the ground state of the problem Hamiltonian. In this case, we try to use the Rydberg optimizer, where green represented by blue color, R1 represented by green, and R2 represented by orange color, and do the sweeping protocol like this one, which is the determining sweep from big negative value to big positive value, but the Arabic frequency stay constant. And this sweeping direction, so basically we just sweeping to this one, t equal to 0 here, and end up in this position. But first one, we only consider the problem Hamiltonian, which is graph curving problem Hamiltonian, by turning off the Rabi frequency here. You can see we turn off the Rabi frequency. And do the additive evolution, you can see that the annealing state just stay at its classical trajectory. Basically, this ground state this as the initial state here, they are actually the eigenstate of this Hamiltonian. And when we do the additive evolution, it's just actually stay at the eigenstate trajectory because they are eigenstate of this Hamiltonian. But if we add the quantum mixing term, which is turned on the Rabi frequency right now, there will be the energy splitting. So you can see that original, they have two level crossing between this classical energy level. But once we add quantum mixing, they become split up. And when we perform the sweeping again, we can see that the quantum deadening state starting from the atomic ground state here will end up in the graph carrying state that we are looking for. This is in quantum optics, we call it Landau-Sinner transition. And the omega I here play a very important role, such that they split the energy level of this two level crossing of the classical energy system. And it's come to our optimization protocol in the Rydberg system. So if you have, for example, this graph, we want to solve graph carrying on this triangular shape triangle lattice here. We map them, for example, each vertex are mapped to each atoms here, and carefully choose each connecting atom to be in the bucket radius of each other to implement the edge between them, and then run the adiabatic sweeping protocol as I have mentioned before. So this is our adiabatic sweeping protocol with the red line here as a detuning sweeping and the blue line here as a omega Rabi frequency, and we slowly tune it to be slowly enough to make sure that our adiabatic evolution is still working. And then we can see that at the end of the time sweeping here, the state that we are probed in the quantum annealing become the graph carrying solution. But in this case, if we measure them, we can see that we got the sixth degeneracy, or it means that we got more than one solution, where all of the six solutions here actually have the degenerate energies due to the graph symmetry itself. You can see that because the triangle graph have the six degeneracy, because we can have some kind of like rotation with pi over 3 degrees, and we can have 3 rotation, and they also have 2 reflection between them. So basically they have 3 times 2 degeneracy, which is got you 6 degeneracy as this graph carrying solutions. So in our work, we just consider the simple graph, which the equidistant structure you can see. I will explain you a couple of later why we need this equidistant. It will be very useful in our Hamiltonian in some sense that they suppress unwanted internegative interaction, but I will explain it later. And we solve it with the 3 Rydberg states, 65, 70, 25 in the rubidium atom in the S state here, and use ground state, Rydberg state 1, Rydberg state 2, Rydberg state 3, representing each color here, and do the sweeping protocol with the same, with the fixed Rabi frequency turned on and the slowly sweeping as a cubic function for the detuning, and we can solve all the graph carrying problem like this one. So you can see that all the graph problem can be solved quite robustly with the degeneracy depending on the graph symmetry itself. You can see that if all the neighboring atoms here are never excited to the Rydberg, the same Rydberg state, because the same Rydberg state will block the neighboring atom to excited to the same Rydberg state, as this is the blockade mechanism that have been mentioned before. So for example, this vertex are excited in the yellow Rydberg state. So these two neighboring atoms can never be excited to the yellow Rydberg state. So they can only be excited to the orange and green. And this works for every graph here. Something is interesting about solving this triangle shape. So right now, if we plot the instantaneous eigenenergy spectrum of the Hamiltonian that depending by time, we can see that, for example, this six degenerate graph solution here, if we plot their energy level line, it turns out to be almost the same energy level as the blue line here. You can see at the end of sweeping here, which is actually this blue line energy are combined all 6 degenerate states to each other, which is actually the consequence of the S3 symmetry they have. Something very interesting happen here because you know that our pain point of quantum annealing is that the gap will be closing as long as you have increased the system size. So basically this gap will be closing exponentially fast with the system size increasing. But if you have this symmetry in your system, somehow the energy levels will be encouraged to combine with each other due to its symmetry and make the energy spectrum more separated. Some highlight they have some gap between each energy spectrum here, which might be provide some advantage over this quantum annealing algorithms. And if we consider more a bit carefully, some kind like except apart from the sixth degenerate state, we also get a very low fidelity of this state. And actually, you can see that this state is actually, you can see for the orange set here, they are excited in the corner of the triangle shape. And these orange sets are actually maximum independent set. But somehow this maximum independent set are not belongs to our optimal gap carrying solution. On the other hand, in contrast, the orange set in this case, they are maximal independent set. So this is why that hybrid algorithm, which is solved with classical solver, a half and other half with the quantum machine to solve maximum independent set, that hybrid classical algorithm could use this not optimal gap carrying solution. But if we use quantum annealing algorithm, it makes sure that the solution that we get at the end of sweeping time will be optimal gap carrying problem that we are looking for. So I need to explain about the Rydberg physics between the Rydberg-Qudit system. So basically, this is our system. And we have the individual atomic Hamiltonian energy, which is quite familiar for all of you, I think. And this is represent the energy of the individual atomic atoms. And we have detuning 2 and detuning 1 representing the energy of the Rydberg state 1 and Rydberg state 2. And we have omega 1, omega 2 associated with the coupling with the sigma 1 and sigma 2 here. Sigma 1 is actually the analogous to Pauli X matrix, but act on G and R1. Again, same for the sigma 2, they are act on G and R2. N1 and N2, just the projection operator. And van der Waals interaction, because we have right now in this example case, we have two Rydberg state R1 and R2. So basically we got R1 interaction and R2 interaction scaling with the C61 and C62 respectively. So don't forget about this divided by R to the 6 at the interatomic distance between psi I and psi j. And because the orange and green can have interstate interaction as well, this interaction is unnecessary. We don't want this interaction to solve our gap carrying problem. But fortunately, this C612, if we choose the NS state, it means the angular momentum equal to 0, this C612 are normally very small compared with C61 and C62. So we allow them to exist in our system if we assume that, if we ensure that these C612 are very small compared to this C62 and C61. And actually, they have another dipole exchange interaction which allow the flip-flop dynamics between R1 and R2. But if we choose two Rydberg state R1 and R2 to have the same parity L1 equal to L2, it means that this flip-flop interaction or resonant dipole interaction can be ignored. So this is very important that we choose two Rydberg states to have the same parity. It's very important. It's very key ingredient for our Rydberg system to solve our gap carrying problem. And about the Rydberg bucket, I think because I suppose all of you here come from the Rydberg field, so I will go it very quick here. So if you have the pair of interaction of the green Rydberg atoms here, the second atom can be excited to the green Rydberg state once they are separate far away, far than the bucket radius. But once they move to the Rydberg bucket radius at this point, and the energy of this pair interaction become equal to energy gap here, which I will explain later. They become blockade if you move it, if you move further. The same principle apply for the orange pair interaction. So if you have the first atom excited in the orange Rydberg state here, the second atom can be excited to the orange Rydberg state if they are separate away far than Rydberg bucket radius 2. But once they move to have the pair potential energy equal to energy gap as well, they become blocked. And if you move further, they will be blocked effectively. This is the condition of the Rydberg bucket, is that you need to have pair potential bigger the epsilon gap. And by this condition, it allows you to have the Rydberg bucket radius defined by this definition. For the interatomic state interaction, they have the same principle, but in this case, as we choose NS state, some kind like R1 and R2 to be in the NS angular orbital momentum state, the C612 that you normally get will be negative. So only the bottom curve that we will consider and just ignore the below curve. If you have the first atom excited in the green, for example, the second can be excited to in orange. But if they move to the point such that the pair interaction become equal to 0, which is equal to this product of the atomic ground state here, it means that right now, if you move further, if you move a bit further, this pair interaction will have a negative energy even lower than the atomic ground state itself. And in this case, the additive sweeping will never cross with this state, and this state will never happen. It means that they have a blockade condition, but this is the forbidden scenario. We don't want this scenario to happen. So, which is why we need to have atom lattice spacing to be greater than RB12. Be reminded that because C61 and C62 are positive, so the force between the same species Rydberg state will be the positive force. But if the pair potential of the different Rydberg state here, the force between them will be the attractive force because the C612 is negative. We remember that right now we shoot the Rydberg state only in the NS state. And the last one will be Rydberg-Thom graph encoding. So as mentioned, we have this is the Rydberg-Qudit Hamiltonian. And if we choose the equidistant structure, this interstate interaction can be ignored. You can see we just use the dim shade here to represent that this right now in this situation with the equidistant structure, the C6ij becomes significant. Why it can be ignored in this case? If you can remember, I will the couple few slides I have shown that C612 is actually, even though they are negative, but they are much smaller than C61 and C62. And if you have the denominator, which is the interatomic distance, the C6 over this interatomic distance R to the 6 will become big for the C61 and C62, but become small for the C6ij. So the only thing that we need to do is that we just adjust the lattice spacing to be in this interstate Rydberg pocket and to be less than the intrastate Rydberg pocket here. And the tuning just adjust them to be less than the penalized interaction term but bigger than the interstate interaction term here. And in this case, we can, okay. But if we want to tune the non-equidistant, for example, this graph, it means, for example, this graph are actually non-equidistant because right now the atom 5 and atom 3, atom 4 and atom 2 and atom 4, they are connected to each other, which is we actually implement the next nearest neighboring edge. In this case, this interaction will become significant because this short edge can have C6ij interaction become significant because right now the denominator, which is the interatomic distance, R to the 6, become much greater, much smaller than a square root 2. It means that the C6ij of this 2 and 3 pair will become significant or comparable with the interstate interaction pair between this between this long atomic pair. And in this case, we need another condition to be prepared because sometimes the atom 5 and atom 3 or the atom pair in the long distance here can become blockade violation because there is a compensation of the negative energy from the interstate interaction here. So that's why we need another condition here to make sure that there is a blockade between next nearest neighboring atom pair. And to solve this problem, we solve the same graph, but we move if you remember, we move the atom 4, for example, this one. We move the atom 5 in 3D. Sometimes I move this atom 5 in Z axis to make it 3D, like this one. And right now we can find the equidistant structure. And if you have the equidistant structure, this interstate interaction become insignificant again. And solve the graph curring of this graph will give you a very optimal graph curring solution with high fidelity again. And all thing we need to do is just adjust the lattice spacing to be in this blockade regime window and have everything to be greater and less than this two interaction term. And you solve the graph curring problem by the same-parity protocol. It gives you very robust graph curring optimal solution with high fidelity. So equidistant structure is the answer if you want to insist on using this Rydberg vertex to atom mapping here. And if you want to solve the non-equidistant graph, for example, the first three graphs here are complete graph. You can see that, for example, you run the solution for the first triangle shape complete graph and square shape complete graph, just only consider on the A and B here. You can see that they have a noise solution. You can see they have a red solution here with quite a fidelity, make the overall optimal solution not going to the very high fidelity. And this is because there exists the long and short long and short edge, which allow the negative interstate interaction potential tail to be significant and affect the ground state of system. But if you choose some kind of move the vertex here in 3D, make it tetrahedral graph like this one. So right now you are encoding the graph in 3D dimension already and solve the gap clearing problem again. You can see that we got the gap clearing solution with very high fidelity to 97 and 98%, and you got a very beautiful S4 symmetry. In this case, you can claim that actually this ground state of this tetrahedral Rydberg-Qudit system effectively generate the pot ground state with the highest order degeneracy 4 fact, which is the 4 fact which is equal to 24 degenerate state, as I mentioned here. And also I solved the gap clearing for the non-equidistant graph as a pentagon graph here, because right now the short edge and the long edge are quite comparable compared to this A and A square root 2. This A and 2A sine theta over 2 are incomparable much more than this square case. And when you run the gap clearing problem again, you get quite the optimal solution with the high fidelity, with no not much noisy state with this incorrect gap clearing solution. So what's happened if we have C6ij very small but less than 0? So I plot the eigenstate of the system of the square and the system of the tetrahedral here. You can see that the ground state, sorry, just accidentally put this one. The ground state here will be interrupted by this interstate interaction. You can see that the ground state of this square shape complete graph are actually the C2 state, because the interstate between orange and yellow here are actually negative, and because the distance between them are very short, it makes the C6 over R to the 6 become very big negative value. So that's why they make the ground state of the system to be goes to minus 102 pi megahertz here. But if you move one atoms to be in 3D, some kind like this one, make the same graph with the same connectivity in the 3D embedding here, you can find that right now in the ground state will be the graph carrying state with no conflict edge here with the fidelity 98.7%. So you can see that to elevate this problem from C6ij, we can use the 3D embedding to make the equidistant structure and suppress that interstate interactions and get the correct gap clearing solution with high fidelity. So let's see if we have C6ij equal to 0, which is maybe ideal state, but we can explore in the future. If we have C6ij goes to 0, basically, even you have the square shape of the graph with the long and short edge, you can get the very high fidelity of the gap clearing solution. Of course, you can still get some very small noisy state here, but it would be much better to have the two Rydberg state with the 0 interstate coupling. But in real life, in experiment, it's still very hard to find the ideal two Rydberg state with no interstate coupling anymore. But if any one of you know the solution, some kind like you have the system with the interstate coupling very small compared to the intrastate coupling, just email me and we can develop more platform to solve the gap clearing problem with this neutral atom platform. So the summary. So sorry for spend a long time to this one. So we can solve the minimum vertex gap clearing problem for the K chromatic gap with n vertices with n atom of with K Rydberg-Qudit n atoms here. So if you have the graph which is K chromatic, it means that at least this graph need to have K color to solve the gap clearing problem. We just only need n K Rydberg-Qudit atom to solve them robustly. And for planar graph, you can use unit graph by vertex atom mapping or non-unit graph. If there are non-unit graph, we can use the technique of the Rydberg quantum wire method. Some kind like you have the planar graph like this one, and you implement the auxiliary atoms at the quantum Rydberg quantum chain and run the quantity sweeping. You can get the solution of the gap clearing problem as well. For non-planar graph would be more challenging because Rydberg quantum wire can be applied in this case, but the interaction tail needs to be considered at the edge. And or if you want to elevate the interstate coupling, which is unwanted interaction, we can use 3D embedding to solve the problem. And this is more interesting stuff. You can study Rydberg physics with the Qudit system, but I will not go into detail because we have goals a long time. Yeah, and thank you very much for listening to the presentation.
Thank you, Tuna, for your presentation. So it's time for question more discussion, comments? Are there any questions from audience? So I have a question. So that I think basically two proposal of to implement the 3D placement
Yeah.
of the cold atoms, as well as we want to add more laser beams.
Mm-hmm.
So which, for example, do you have any comments on the feasibility in terms of the experiment, or for example, which is much more easier or harder to implement in experiment, or
Yeah.
any other evidence at this point?
I would say that's a very good question actually, because one of the collaborators, Jonathan Pritchard from that class, he is experimentalist, and he said that it's still very hard to implement Qubit state, because the more Qubit state we need, the more laser we need to apply to the system, and the more lasers mean that they can have some intercoupling between them, or make the decoherence come even earlier in the system. So I think this supposed to be the problem of the technologies of the optical lasers. So if we have ability to can actually have more lasers to accurately control each individual DOM better, we maybe can implement this system with the Rydberg-Qudit state. But at the moment, I think it's still would be very challenging. But I think there is a lot of group in that have done this Qudit state with the microwave laser. Sometimes they apply the microwave laser to drive between the coupling between each Rydberg states, which is actually Charles George Adam, my supervisor. His group is actually perform the microwave driving between Rydberg states, and that worked quite effectively in our lab right now. But in this case, we have 4 lasers to coupling, 2 of them coupling ground state to R1, and another 2 of them coupling to ground state to R2. So basically, we are doing the coupling from the ground state. Both of the lasers are coupling from the ground state, but maybe we can change some kind of like 2 of them coupling ground to R1, and then 2 microwave lasers to coupling R1 to R2, and that scheme should work as well for the system. Yeah.
So how about the 3D placement?
3D
It's
placement.
also,
Yeah, that's a good question, because this work is numerical works. So basically, I can adjust the geometry of the graph as I want, right? So basically, you just computationally calculate the geometry like this and calculate the Hamiltonian. But to do that in experiment, you need optical tweezer chamber. You need to have more advanced the chamber to trap each atom with this optical tweezer array, but can ability to tune them in 3D as well. So I think that would be more challenging in terms of the experimentalists. But I think as the time goes by, I think in the future they can implement this 3D optical tweezer array trapping. Yeah, it should not be a problem, I think, because they have been that in the optical lattice before, right? We have the 3D optical lattice with the laser in the 3D arrays, and optical tweezer array should be fine. I'm not sure because I'm not experimentalist, but I think it shouldn't be a problem. Yeah, for the future. Yeah.
hey, thank you. Any other questions, comments? No. So, Sunat, thank you again for your presentation.
No, welcome. You're welcome. No worry. Yeah, I'm very glad that I have a presentation here, and we need to sorry if I have spent a lot of time. Yeah, but hopefully, if you have any question, you can just following the works in the archive, or just email me personally. I happy to inquire all the question from you all. Yeah. Yeah.
Hey, thank you.
Thank you very much.
So I'd like, okay, yeah. So I'd like to close the seminar.